Hello everyone and welcome back. So today we're going to be talking about power and efficiency. Power and efficiency. So, you'll be able to determine how the power is generated by a machine and calculate the efficiency of that machine. Now let's jump straight into applications. So, engines and motors are often rated in terms of their power output. For example, the power output of this motor lifting the elevator is related to the vertical force that it can apply to accelerate it to some particular velocity and keep it at that velocity the entire way up. Now, if we know exactly what velocity we want, though, with some sort of maximum load here, because obviously I'm not going to take in the variations, how can we determine the power output we would need, the power requirement of that motor? Well, if it was perfectly efficient, it would just be force times velocity. Magic. We'll get to that later. Okay, let's look at a second application here. So we have a truck and it's going up a hill. And we know the speed at which a truck can climb a hill is going to depend on the power output of that engine as well as the angle of the hill. I mean, if it's that angle, well, nothing that guy's going to be able to do. So, with that in mind, if we know the angle, can we determine the speed of the truck? If we know how much power the engine is transmitting? And could we find the speed if we know that power? And could we find the efficiency of the engine if we know how much energy it was taking in from its fuel? All of these things are important. They're important and they're all going to be coming from power and efficiency, connecting what we've been learning with that new concept of taking kinetic energy of things and how the principle of work and energy allows us to solve problems, and now taking it into putting it over a time frame. It's not just energy, but energy over time, which is power. So, power is defined as the amount of work performed per unit of time. So, if a machine performs a certain amount of work, which we're going to call du, and it's over a given interval dt, then the power is simply this. And since we can write our work as the force of being applied times the change in position, or sorry, the dot with the change in position, we can rewrite this. And we get, well, force dot with dr dt, or change position over change in time, which is simply velocity. And I'm like, oh, yep, there's the equation I was talking about. There's the equation I was talking about. So for this, we realize that power is a scalar. And also that we only care about the components of velocity and force that are actually in the same direction. If I'm pressing down like this and my car is moving this way, I'm not doing any work on my vehicle. And I'm not generating any power. I'm probably wasting energy, and that's just from a different way from all the heat and other forces that are in my body being dissipated. Okay, so if we use our scalar notation, because power is a scalar, we can say, okay, well, the magnitude of force, magnitude of velocity, we can get this right here, where theta is the angle between these two. So, if the velocity of a body acted on by a force F is known, we can determine the power just by taking a dot product. And then our units for this are going to be most often the watt. The watt. That's the metric unit. However, sometimes you will see the foot-pound per second, which is an eyesore. I just like it. However, every once in a while I might throw that at you, so be ready for it. What you'll see more commonly, though, is horsepower, which, interestingly enough, is actually connected to horses. 1 horsepower was technically the amount of work that a horse could do on average in a single day. I have a great example in my intro to engineering class. It just talks about a horse that's having to pull a plow, and the horse is doing it for an 8-hour day, going back and forth for a very, very long distance. And in an 8-hour day, it was able to generate 550 foot-pounds per second of power. So it's a very fun little thing that it actually does come from horses. It's how much work a horse could do in a day. But also, interestingly enough, humans can do more than 1 horsepower a day. We're more powerful than horses. Be proud of that. Okay, how about efficiency? Well, efficiency is the fact that we are not going to be able to use all of our power. Either we're going to lose some energy, you can think about it that way, or just not all of the power actually gets transmitted into doing work. So what we're going to have is we're going to have the power output over the power input, and this is always, always, always less than 1. In a perfect system, it would be equal to 1, but it's always going to be less than 1 in real life. A very common one here is the power input is usually, but not always, electrical power. And that goes into a machine which then has some sort of physical power, like it lifts a block or the motor turns. You might also see power input being from like gas, so like chemical power. But that's not always the case. I'm just saying that that's usually what's going with the input. This class you don't have to worry about that too much, but just don't forget it. So now we can also put this in terms of energy input, like I said. So if the energy you're inputting is going to be different than the energy you're outputting, that's because of efficiency. And once again, this is also always going to be less than 1. There is no such thing as a perfectly efficient system. I mean, we're trying to get there with these superconducting, transistors, but we haven't gotten there yet, at least for normal systems. Sorry, a superconductor is something that can transmit energy or electricity without any loss in energy. But we're not quite there yet. Now, where do we lose this energy? Well, it's usually coming from friction, some sort of frictional force. You have wear, you have tear, you have resistance because it's not made perfect. Lots of different things. If you hear a sound when it's running, that's wasting energy because that's pressure waves going away from it. If it heats up, that's wasting energy, but that's usually coming from friction, except for the cases of like when you're burning gasoline. But all those different things are dissipating energy, and because of that, you're going to need additional power to do the same amount of work. Okay, so that's it for this time. We'll stop here. Thank you for listening, and I'll see you all later. Have a wonderful day. Bye-bye.